So we've talked about modulation, and in that section I talked about time division multiple access and code division multiple access and OFDM and direct sequence spread spectrum, and so I mentioned a lot of terminology. In this next part we're going to take a look, well, what does that mean? And those things are what we call different transmission methods. So we've talked about how I represent my ones and zeros in waveforms, but we haven't talked about how I send my signals out over the air, how I actually transmit in the frequency band. And that's what we're going to talk about here when we talk about RF coding. We're going to talk about direct sequence spread spectrum, OFDM. So let's first talk a little bit about spread spectrum. So spread spectrum is a technique where I use more spectrum than I actually need to transmit the signal. And so you can see in this graph that I've spread my signal over a much wider band, but I could have transmitted it just in that narrow band. And you say, well, why would you do that? Wouldn't that use more frequency? And the answer is yes, it would. But remember that 802.11 wireless LANs were defined to operate in a noisy, interfering kind of environment. So if I spread my signal across a wider band and there's some interference in that band, then the probability of me being able to recover that signal is much higher. And so spread spectrum is a technique that was defined in the early part of 802.11 because they knew that this was a shared spectrum. And it is exactly what is suggesting in this graph, a way of spreading your signal over a much wider band when it's transmitting. There are two types of spread spectrum technique. The first one's frequency hopping spread spectrum, and Bluetooth uses that. And the second one is direct sequence spread spectrum, and this is used by 802.11b. It's also the technique used by Zigbee that we talked about earlier. Now, frequency hopping, what that does, and the name might suggest it, is it literally hops across a wide band. So it transmits on this frequency for one moment, jumps to another frequency, transmits there, hops to another frequency, transmits there. Now, the pattern that it hops in needs to be known so that the receiving side knows what frequency it should be listening to. But if it hops to a frequency that suffers some interference, it could lose that part of the signal, but then it's going to hop to another one, and then the probability is that something else isn't there, and you'll be able to get that part of the signal. So it literally hops across the frequency band, so it hops over a wider band in order to give it diversity on the frequency so it can operate in an interference-orientated environment. So direct sequence spread spectrum used in 802.11b is a way of applying a code to the bit stream. So I literally take your ones and zeros and apply a code. And what that does is it increases my bit rate. So let's say your traffic was at 1 megabit per second, I apply a code and you end up at 11 megabits per second. And you say, well, why do I do that? Well, because if I transmit at a higher data rate, where each of those bits is at a lower power level, what will happen is my signal will spread, like we saw in the previous slide, across the band. And because I've applied these codes, I'm transmitting many, many more bits than your original information bit. And so if I lose a few of the bits because something's interfering, I can recover from it and I can still get back to your original bit. So it's a concept of applying codes and spreading the signal over the band. Now, it's important to know that 802.11b uses direct sequence spread spectrum, but it is the older technology. And it was great, but now we're moving to OFDM. And this is a much more important technology to try and understand when it comes to Wi-Fi. And 802.11a/g/n and the newer standards, AC, all support OFDM. So OFDM is simply a different technique than spread spectrum, and is a more complicated technique. Sometimes the radios therefore tend to be a little bit more expensive, But the benefit is that in the same spectrum, the same frequency channel, I can get up to higher data rates. And given the increasing demand on our wireless networks, I want to get up to the highest data rate I possibly can in the given spectrum, because that bandwidth is really needed, especially with all the video streaming that's going on over our wireless devices today. So OFDM, and here I'm looking at a picture of 802.11n, and what OFDM does is it says, oh, well, let me take a frequency band, and in this example I've got a 20 megahertz channel, and let me slice it into smaller subcarriers. And in this example, I've actually sliced it up into 64 subcarriers, 48 of which are shown here that actually carry data. And again, here I'm looking at 802.11n. Okay, so basically each one of these is going to carry a bit stream. So you can think about this as this one carrying bit 1, this one carrying bit 2, this one carrying bit 3, this one carrying bit 4, etc. So each of these individual subcarriers is going to carry data. Hence the term frequency division multiplexing. I slice up the frequencies, I divide the frequencies, and I multiplex my data onto the frequency channel, i.e. I'm sending multiple bits on different frequencies at the same time. The secret of this technology is that it's orthogonal, and you'll see here how the signals overlap with one another, and see how this signal here is a null while this one peaks. That's the property of orthogonality. So I can literally get the signals to overlap and not interfere with each other, which means I can get lots of subcarriers really close together, and that means I can get up to super high data rates. So we've talked about direct sequence and spread spectrum, and this is orthogonal frequency division multiplexing, just different ways of transmitting over the frequency channel.